All right, AP Calc 5.7 deals with a concept here called U substitution. And this is one of the two big methods that we have for evaluating integrals that are a little bit more complicated beyond what we've been seeing up to this point. Up until now, we have basically been able to evaluate integrals by simply reversing the process of differentiation. And of course, that word is anti-differentiation. That's really the process we've been using. But in certain cases, in fact, problems like we're going to be seeing today, the integrands we're going to be dealing with are going to be more complicated than what we've seen before, and simply reversing the process of differentiation isn't going to work. So that being said, let's dive into our first example. We're looking at an indefinite integral of a trinomial, 3x squared minus 5x plus 2, raised to a power. Haven't really seen that before. And then it then gets multiplied by a binomial of 6x minus 5, all taken with respect to x. This is considerably more difficult than anything we've done up until this point. Now, I do just want to make a quick mention of one important thing. We are being asked here, everybody, to take an indefinite integral with respect to x. And one of the things we discussed a while ago that I want to make sure that everyone understands, the answer to an indefinite integral is going to be a function. We are going to have x's in our answer. Now, later on today, we're going to be looking at some definite integral problems. And the answer to a definite integral problem was, and still is going to be, a constant. Something like 7 or 3 pi, all right? But an indefinite integral, we're going to end up with a function for our answer. And the nice thing about doing indefinite integrals is when we get done, when we come up with an answer, we're going to be able to check that answer by taking the derivative of our solution, and hopefully that derivative will come back and equal the original integrand. And if it does, we'll know that we've done our job correctly. Now, let's talk about why this is different than what we have been doing in the past. In the past, we've simply been walking through the integrand and reversing the process of differentiation. So please do not write this down, because what I'm about to do is 100% wrong. But here is what a person, maybe even a smart person, would think. All right, in my integrand, I've got something cubed. So I'm going to take the same base, which is going to be 3x squared minus 5x plus 2. I'm going to raise the power by 1, which is a 4. I'm going to divide by that new power, which is dividing by 4, or putting a 1/4, sorry about that, or putting a 1/4 out in front. Then, of course, there's this little problem with the chain rule, where with differentiating, we'd have to multiply now, we'd have to multiply now by the derivative within. Since I'm reversing that process, maybe I would now need to divide by the derivative within, which would be a 6x minus 5. But wait a minute, then there's this whole other factor of 6x minus 5, and if I anti-differentiated that, that would get me a 3x squared minus 5x. Okay, there's my antiderivative. There's only one problem with this, everybody. If you were to try to take the derivative of this answer, it would not get you anywhere close to the original antiderivative. To prove that to you would probably take another 5 minutes. So I'm going to ask you guys to trust me on that. But this method of thinking doesn't work. And basically, let's shut up and let's get down to some really important information right here. What I want you guys to recognize is that this original integrand is more complicated than what we've done before, and there's one important thing here. So here's a question which seems counterintuitive, but hear me out. If we were being asked to take the derivative of this integrand right here, would it require one of the more complicated rules from back in Chapter 3? And the answer to that is yes. This function would require the product rule if we were going to try to differentiate it. And if its derivative would require the product rule or the quotient rule or the chain rule in a way that involves your variable at any one of those steps, then it is too complicated to anti-differentiate simply by reversing the process of differentiation. You'll hear me say that a few more times before we get done here. So that's really the first step, recognizing that this is a complicated problem that cannot be done with normal anti-differentiation methods. So what we're going to do instead, guys, is talk about this method here called U substitution. And U substitution is a method we are going to use when the answer to the following two questions here are both yes. First question, does your integrand contain two distinct parts? Well, there's one of them, a trinomial cubed, and then it's multiplied by a binomial. So yeah, our integrand contains two distinct parts. Second of all, are those two parts related to each other in some way? Is the derivative of one of those parts going to equal the second part or get you something close to it? And I don't know if you guys noticed this or not, but the derivative of 3x squared minus 5x plus 2 would be 6x minus 5. That's not a coincidence. That is the only reason a problem like this works out. So what we're going to do then is start this process of U substitution by letting part of the original integrand equal U. And what a student said to me a long time ago is this: you want to let U equal the easier part of the harder part. So again, two different parts to the integrand. There's the first, there's the second. The first part is definitely the more complicated, the harder part. The 3x squared minus 5x plus 2 cubed. We're going to let U equal part of that. Not the hardest part, which is the cube, but the base of that exponent. The 3x squared minus 5x plus 2. So, humor me here, guys. Let's see where we're at here now. This integral now is the integral of, and this entire first polynomial here, this trinomial, got it? The 3x squared minus 5x plus 2. We've replaced all that with a U. All right, and U is still being cubed. So that is what we call our primary substitution right there, guys. That is what U is actually equal to. Now, what we still need to work on is what's called our secondary substitution. We need to get the 6x minus 5 and the dx, that's important, both expressed in terms of U as well. And the way we're going to do that, and luckily we do this the same every time we do it, is we're now going to take the derivative of this little equation right here. Now, technically, you might not want to write this yet. We're going to take the derivative of U with respect to x, and that is going to equal, the derivative of the right-hand side is going to be a 6x minus 5. But what we really need, you guys, is 6x minus 5 multiplied by dx. And I can get that from this equation that I just wrote on the bottom, but that dx I'm going to move to the other side with multiplication. So what I'm actually going to do here is just call the left side du and the right side 6x minus 5 dx. And technically there should be parentheses or brackets right here, but we'll normally leave those off. And now I hope you guys see it. 6x minus 5 dx is exactly what we still needed to cover here with our secondary substitution. So reading this backwards, 6x minus 5 times dx is equal to du. So the 6x minus 5 dx right here just gets replaced by a du. And look at how much simpler now this new integral is to evaluate than what we started with. Again, let's be clear on what we've accomplished. The integral just came right down. The 3x, dang gummit, the 3x minus 5 dx, 3x squared minus 5x plus 2 quantity cubed, that became U cubed. And the 6x minus 5 dx, all of that got replaced with du, and all of that information came from this little bit of work I did in green over here on the right. And now, this is an incredibly easy integral to evaluate. Integrating a U cubed with respect to U is going to give us a 1/4 U to the 4th, okay? And of course, there'll be a plus C at the end of that because it's an indefinite integral. And the only thing we have to do now, guys, is recognize that the original problem was given to us in terms of x. We've given them an answer now in terms of U, so we need to resubstitute or unsubstitute, if you want to look at it that way. We need to put this 3x squared minus 5x plus 2 back in the place of U. So that'll be a 1/4. U is the quadratic trinomial of 3x squared minus 5x plus 2. So there's your U to the 4th power and a plus C. And everybody, it sure looks like, or I sure think, that is our answer. But lucky for us, as I said a while ago, we can test this answer now. Let me see if I can shrink this down a little bit. If I draw something here, then I think I can zoom back in. Yeah, there we go, and get where I need to be. Okay, we can test this answer now, you guys, by taking the derivative of our answer and making sure that it equals the original integrand. So that derivative would be a 1/4 out in front. Then we multiply this exponent down, so 1/4 times 4. The base stays the same, so that's going to be a 3x squared minus a 5x plus 2. We drop the exponent by 1, so that's 3, but wait, there's more, times the derivative within. And the derivative of 3x squared minus 5x plus 2 is going to be a 6x minus 5. And what happens now? The 4 and the 1/4 cancel each other out, and that is the derivative of our answer. And sure enough, that matches perfectly the original integrand we started with. So at this point, everybody, I feel supremely confident in that answer right there because we tested it and it did the thing that we needed it to do. So everybody, that's U substitution in a nutshell. When your integrand is really complicated, when it contains two distinct parts that are somehow related to one another in terms of one being the derivative of the other, we're going to let U take the place of the more complicated part and then make that substitution here with du as well. And the hope would be, this line right here was really important, the hope would be then two things. That A, we can represent all of our x's, including the dx, in terms of u's and du. And second of all, that the new integrand that we create through U substitution is easier to evaluate than the one that we started with. And that certainly happened here. Okay, let's move on to another example, everybody. This one looks a little bit different. We're doing an integral of a fraction now, all right, a function with x's on both the top and the bottom. And on top of that, there's a radical on the bottom as well. So you're going to ask yourself the same two questions every time. Number one, are there two distinct parts to my integrand? Well, it's pretty obvious with a fraction, guys. There's a top and a bottom. So yeah, there's two distinct parts. And is one of them the derivative of the other or some way related to it? So the question becomes here, what would we let U equal? Well, maybe you see it, maybe you don't. The more complicated part is the bottom of this fraction, and specifically the radicand. And we've got a trinomial there of 4 plus 8x minus 2x squared. The derivative of that radicand would be an 8 minus 4x. I'm going to just doodle that real quick here, an 8 minus 4x. And if you compare that to 24 minus 12x, I could get there from here if I were to just multiply by 3. Let's keep that in mind. So this one isn't going to work out quite as nicely as the last one, but we're going to be just fine on this one. So again, everybody, when this happens, we are going to let U equal the easy part of the hard part. The hard part is the bottom. The radical is the hardest part of the bottom, but the radicand, the 4 plus the 8x and the minus 2x squared, that's going to give us what we need here. So I go back and forth as to whether I'm going to do this at once or keep going on the U, but let's see where we're at right now, guys. We now are taking the integral. All right, you know what? This is starting to get old. All right, equals the, and I just did it again, I think. I'm struggling here, guys. Equals the integral of, here we go. So we've got a fraction. And down in the denominator, we are now taking the square root of, and that whole trinomial just got replaced by U. I don't like that U, so I'm going to redraw it, but it is a U. All right, that's what we call our primary substitution. Now, our secondary substitution is all of this. We need 24 minus 12x times dx, represented in terms of U's and du. And the way we are going to do that, we are going to differentiate both sides of this equation that we just came up with. So learning the shortcut I came up with on the last one, this is now going to be du. I won't bother writing du over dx because I'm just going to move the dx anyway, equals, and the derivative of 4 plus 8x minus 2x squared is going to be an 8 and then a minus 4x multiplied by dx. Technically, there's parentheses around the 8 minus 4x, but we really don't need that if we can just remember what we're doing. Now, take a look at where we are right here, the second line that I drew in green, and compare it to this circled red expression here. In green is where we are. In red is where we need to be. And we can get there by multiplying both sides of this entire equation here by 3. So what does that do for us? 3 times du is equal to, and I'll distribute that 3 in there, a 24 minus a 12x and a dx at the end of all that. And everybody, that right there, 24 minus 12x dx, is exactly what we needed to have covered right here. So let me switch back to purple. Let me talk again about where we're at with our substitution process. We made our primary substitution in the denominator, right? The 4 plus 8x minus 2x squared just got replaced by a u. The square root is still there. But everything else that's circled in red, 24 minus 12x dx, is right here, and it can be replaced by a 3 du. Now, it's going to be tempting to just go in order and just put the 3 du right here, and that's 100% right. But I'm going to try to be a little bit smarter about this and remember where it is that I am going with this. The 3, everybody, is a constant, and the constant multiple rule for integrals says that I can pull that out in front of the integral and simply worry about it later. The du is the variable of integration, everybody. So what I'm going to do is put that at the end of the fraction. Dang gummit, that happened before one time. That's weird. All right, and put that du right here at the end of that. And now I'm erasing while I'm writing. This is really strange. There's du. And if nothing else is there, we'll just put a 1 in the numerator. Everybody, that's our substitution right here. Primary substitution on the bottom, secondary substitution on the top. And once again, we've accomplished our 2 goals. Number 1, all of the x's have been replaced and represented in terms of u. And second of all, I do believe that this new integral is easier to evaluate than the one that we had originally. I am going to rewrite this one, though, in just a moment right here. 1 over the square root of u, I'm going to write that as u to the negative 1/2 power taken with respect to u. I think that will be a little bit easier to deal with. Okay, now let's go ahead and anti-differentiate. We're going to keep our base the same of u. We're going to raise the power by 1. Negative 1/2 plus 1 is 1/2, and we are going to divide the old coefficient by the new exponent. 3 divided by 1/2 is the same thing as 3 times 2. That's going to give us a 6 out in front. So 6u to the 1/2 and a plus c at the end of all that because we're dealing with an indefinite integral. And then from here, let me do that and this. All right, that did what we wanted it to do. Now we just need to unsubstitute, everybody. I'm going to make this 6, and because the original problem was given to me with a radical, I'm going to put a radical in my answer as well. So instead of a u to the 1/2, I'm going to make that a square root, and u, represented in terms of x, is a 4 plus an 8x and a minus 2x squared. A plus c at the end, and that, everybody, should be our answer to this second example. I would love to take the time, you guys, and differentiate each answer that we come up with to make sure that it's equal to the original, but I'm a little short on time because I got a class starting here pretty soon, so I'm going to ask you guys to trust me on that, or better yet, verify that on your own. All right, but that's where we stand there for example 2. Number 3. This is kind of a famous problem in Calc 1 here, everybody. Let's take a look at it. The integral, and boy, what a poorly drawn integral sign that is, of tangent of x dx, otherwise known as the stan x dx problem. Somebody brought that and pointed that out years ago. Now, the 2 questions I've been asking you so far, right away, we kind of seem to have a problem here. Number 1, is the integrand, or does it exist in 2 distinct parts? Okay, that happened in problem number 1. 2 x polynomials being multiplied together. In number 2, 2 x polynomials kind of being divided and with a radical thrown in there to boot. But this one doesn't really look like that, does it? Well, it can be made to look like that. Right now, guys, I need you to recognize we never learned back in the first semester that tangent of x was the derivative of any trig function that we ever dealt with back then. All right. We learned the derivative of tangent was secant squared. We learned that what? Cosine was the derivative of sine. Negative sine was the derivative of cosine, but never in the first semester did we say that the derivative of this trigonometric function is tangent of x. So you can't simply reverse the process of differentiation. So what are we going to do here, guys? I'm going to put an equals. I'm going to rewrite my integral sign right here, and we're going to rewrite tangent of x in a way that looks a little bit more like what we've been doing earlier. And I'd love to ask you guys if anybody knew where we were going with this. You can change tangent of x into the sine. Okay, you know what? I'm about to order myself one of those gloves right here, you know? You know what I'm talking about. The sine, I'm really struggling here, guys. Boom, boom. You go away, you go away, you go away. Come on now. The sine of x divided by the cosine of x. Usually you'd go in the opposite direction with this. You would change sine of x over cosine of x into tangent, but this actually suits our purposes here better, to write it as a quotient of sine of x over cosine of x. Now, do we have two distinct parts to the integrand? Yes. And is one of them the derivative of the other one? Yes. So the problem here becomes, which should we let u equal? Well, do me a favor and drop your pencil for just a second, everybody, and let me show you why this, which is actually what most people want to guess, doesn't work. If I were to let u equal the sine of x, this would become the integral of u over, and look at what's left over now. We now need to take dx divided by cosine of x. That is not cosine of x times dx, everybody, because the cosine is on the bottom. And if I went and differentiated this, I would get du is equal to cosine x dx. That is cosine of x times dx. What we needed here is dx divided by cosine of x. And it sounds simple, but you cannot manipulate this little equation here in green and get it so that dx divided by cosine of x equals anything in terms of u. So letting u come from the numerator, the sine of x, didn't work out. Then go ahead and grab your pencil, everybody, and let's try the alternative. Let's let u equal the denominator, which is cosine of x. And if I do that, where are we? The derivative of u then becomes, and the derivative of cosine of an angle is the opposite of sine of the same angle with a dx at the end. Now this is almost perfect here, guys. I should have, let's see, let me go back to okay, let's do this. Equals, here we go. So this is now an integral of the denominator, which was cosine of x, that just becomes u. And then what we were trying to represent with our secondary substitution is sine of x times dx. I'm very close to that over here in green if it were not for that stupid negative. So I'll just divide both sides by -1 and get negative du is equal to positive sine of x dx. And that is the secondary substitution that we needed. So everything else here in red, the numerator, the sine of x dx, can be replaced by a negative du. So let's think about where we're going to put those things. The negative, I'm going to put all the way out in front. The du is going to come at the end, and once again, I'm going to put a 1 there up in the numerator because there's nothing else to go there. So have we accomplished two things? Number one, have we replaced all of our x's, including the dx, from the original integrand in terms of u and du? Yes, we have. And second of all, is the new integral easier to evaluate than the one that we started with? And the answer to that is yes as well. And I'm hoping you guys recognize this here. Integrating 1 over x with respect to x, that is the natural log of the absolute value of x, or in this case, u. So the negative comes along for the ride, and integrating 1 over u is going to be the natural log of the absolute value of your denominator, which is just a u and a plus c at the end of all that. And the last thing we need to do now, guys, is get rid of that u and express it back in terms of the original variable here, which is x. So this is going to equal the opposite of the natural log of the absolute value of cosine of x plus c. And that is our answer, everybody, to the infamous stan x dx problem. And if you notice that little thing right there, at one point during class discussion one year, I can't even remember when, somebody said that would be kind of a cool license plate. And so I think I looked it up. Let's see if I can get this to work on the iPad right here. And if I click on that, all right, there we go. Yeah, you can actually check on the Illinois Secretary of State's page there to see if a license plate is available. That one was available. So if you guys are looking for a nice present for Mr. Fontana for the end of the year, there you go. I could get a stan x dx license plate. How cool would that be? Only select people would realize what the heck you were talking about there. But anyway, that's that problem. All right, guys, I've got 3 more to do with you, and guess what? They get a little bit harder. All right, so number 4 I showed you earlier. This is the first definite integral that we are going to do with U substitution. Though, why is U substitution necessary? Because yet again, there are 2 distinct parts to the integrand, and so differentiating this would require the product rule. That's my way of knowing, everybody, that it's too complicated to simply reverse the process of differentiation. We've got to look for another method. So, same 2 questions. You should be sick of hearing them already. Are there 2 distinct parts to your integrand? Yes, there are. Secant squared of x times e to the tangent of x. And is the derivative of one of those parts somehow related to the other part? And I'm hoping you see the connection right there. So let's try it, guys. We are going to let u equal the easier part of the harder part so that the derivative of u will match up with something else in this integrand. We're going to let u equal the exponent on the right-hand side. Okay, we're going to let u be tangent of x. And where are we going from there? The derivative of that now, du, is going to equal secant squared of x dx. And if we think about where we're at right now, guys, let's take a look. This right here becomes your primary substitution. And then everything, there I go, doing it again, and then everything else that's left over, secant squared of x times dx, that's your secondary substitution, and I've got that covered already. So, where are we? Let me go back to purple here now, everybody. This integral could be rewritten as the integral of, and I'm going to leave off those limits of integration for just a moment. The primary substitution right here becomes e to the u power. And then the secondary substitution, everything else, secant squared of x times dx, all of that gets replaced by a du. Now, the only thing we need to consider right now is something that we hinted at a little bit in our 5.6 notes, but I'm not sure we've had time for it to really sink in yet. These limits of integration here, everybody, 0 and pi over 4, are values of your variable, the lowest and highest values of the variable that we're going to consider. And that variable in question is defined by this term, the variable of integration that comes at the end of your integral, which I know a lot of you guys ignore because you think it's unnecessary. Here's where it becomes necessary. 0 and pi over 4 are the lowest and highest values of x in this region, in this interval. But now, we've changed the game here, everybody, through U substitution. We are now integrating with respect to u. So don't write this down. Putting a 0 here and a pi over, danggummit, and a pi over 4 right here doesn't make any sense because those were x values. What I now need are u values. So here's the way we're going to get around that. In addition to changing the integrand and the variable of integration, why is that still there? That's very odd. All right, where were we? Here. Let me just erase that, which for some reason is still there. Okay, in addition to changing the integrand and the variable of integration from x terms into u, we also need to change the limits of integration. And the way we're going to do that, you guys, is we're going to take 0 and pi over 4, which are x values, and we're going to put them into this equation right over here to come up with u values. So how about our lower limit of integration? When x is 0, its u value would come from taking the tangent of 0 radians, which is still 0. But when x is pi over 4, we change that into a u value by taking the tangent of pi over 4, which is 1. And what we've now done, you guys, is we have changed those x values into u values by putting them into this same little machine right here that changes x's into u's by taking the tangent of that x value. Okay, so now we've changed everything, including the limits from x values into u values. So let's go ahead and anti-differentiate. The antiderivative of e to a power is the same base to the same power divided by the derivative of that exponent. Well, the derivative of u, taken with respect to u, is just 1. So we're done now with the antiderivative. E to the u is the antiderivative of e to the u. But because this is a definite integral now, we have an evaluation bar at the end and a 0 here and a 1 here. And now, this is a spot where people run into trouble. In every problem we've done so far, we have replaced this u value and put tangent of x, for example, back in there. But I don't need to do that now. Why? Because we changed these limits of integration into u values. So I can go ahead and evaluate this one just the way it's written. This is going to be e to the first power minus e to the 0 power. E to the first is just e to the 0 is 1, and there is nothing else we can do to clean that up. And that constant, everybody, remember, e is a constant, not a variable. So this constant value is the answer to our definite integral problem. The other thing you could have done, and it is 100% unnecessary, but you could have rewritten this now by resubstituting all of your u values back into x values. So you could have rewritten this as e, the u power now becomes a tangent of x. But if you're going to do that, these values, which we changed into u values, now need to go back to their original x values of 0 and pi over 4. And if you do that, guess what you're going to get, guys? E to the tangent of pi over 4 is e to the 1, minus e to the tangent of 0 is 0, and you're still going to get e minus 1. So it really doesn't matter which way you do it. It's obviously less work to keep doing what I did in purple and keep everything in terms of u, including the limits of integration, and never go back to x in a definite integral problem, as opposed to the 3 that we did prior to this, where it was an indefinite integral problem and you had to go back to x. You can't leave your answer in terms of u because u was a temporary thing that we just came up with. All right, guys, we're making good progress. The last 2 that I have to do with you are kind of unique here, everybody, to your particular book and your particular author. I'll be honest with you and tell you that when we got this new textbook, and I think we got the first edition of it maybe back in I want to say 2010. I was a little befuddled by this problem right here, which is something like this shows up in your homework, guys. I'd never seen a problem like this in a calc book before. Once I saw it, I said, oh, that's kind of cool, and I wanted to talk about it with you guys. So let's analyze it. First of all, does your integrand contain 2 distinct parts? Yes, they're being multiplied together, so a derivative here would require the product rule. That tells me that I probably need U substitution in order to integrate this thing. But here's where it gets weird. Is one of those parts of the integrand the derivative of the other, or somehow closely related to it? And the answer to that is no. But I'm going to dive in here without talking for too long. There's a shocker. And I'm going to go with what I had talked about before. We're going to let U represent the easy part of the hard part of the integrand. So if we're looking at 2 distinct parts to the integrand, I think we can agree the second part, the square root of 5x plus 1, is the more complicated factor right here. And we're going to try to follow the same pattern we've been using. We're going to let u not equal the entire hard part, but the easier part of that hard part. I'm going to leave off the radical and just let u represent 5x plus 1. Okay, hold the phone, Fontana. What have we accomplished right now? And the answer is not very much. So this integral could be rewritten now as the integral, I swear to God, kids. All right. Equals the integral of, and all I've done so far is replaced the radicand with a u. So I still have a square root of u right here, and I guess that is my primary substitution. But now for the secondary substitution, we still need to represent x times dx in terms of u's and du's. So at this point, no reason to think we do anything different than we have been doing. I'm going to differentiate both sides of that equation. But here's where it gets a little bit odd. The derivative of u is equal to, well, the derivative of 5x plus 1 is just 5 dx. And ask yourself, does that match up with what we had here that we needed for our secondary substitution? And the answer is no. In a big way, no. I was really hoping for an x dx right over here, or even a 5x dx, and I could have just divided out the 5. But no, that didn't happen here either. I didn't get an x at all. Now, what I did get that is somewhat helpful is at least a dx. So what this example shows us here, guys, unlike the previous 3 that we've done, is that the secondary substitution, in this case where I need to represent an x dx, the secondary substitution can be done in 2 different parts. We're going to represent the x and the dx separately. So what that means is I'm going to take this equation right here, and I'm just going to, in green, all right, this one right here, guys, and I'm just going to divide both sides by 5 and get a 1/5 du is equal to a dx. And that means, everybody, that this dx right here can be represented by a 1/5 du. Not exactly what I had in mind, but okay. The 1/5 du represents the dx. The one thing we haven't dealt with yet is the x right out in front. We've got to find a way, without reinventing the wheel here, of expressing x in terms of u. And the way we're going to do that is a weird method here, and it's certainly not anything that we've talked about here before. I'm going to take everything that I've written in green, and I'm going to slide that down just a little bit. And what I'm going to do now, you guys, this is weird, I'm going to go up the ladder here. Haven't done this yet. What I have right now on my top line is representing u in terms of x. I want to represent x in terms of u. How? I'm going to simply solve that green linear equation for x. I'm going to subtract a 1 from both sides and get u minus 1 is equal to 5x. And then I'm going to divide both sides by 5 and get x is equal to a u minus 1 all over 5. So, geez, it's kind of ugly, but right there, guys, I now know what to put in right here for x. I'm reading it right off that page right there. X is equal to u minus 1 over 5. All right, so there's 2 questions you need to ask yourself in every problem. Number 1, have we represented the entire original integrand and changed it from x terms into u terms? It's a little bit ugly, but yes, we did. Second of all, is the new integrand easier to evaluate than the old one? Now, the answer to that might very well look like a no, but we can get there, guys. We're going to do one simple thing, and then one thing that maybe is a little bit more complicated we'll talk about in a second. First of all, I see 2 5s on the bottom of fractions right here. I'm going to multiply those together to make a 25, and I'm going to bring that out in front of the integral. So this is 1/25 times the integral of, and then where are we here, guys? I'm going to rewrite this in a slightly different way as the square root of u multiplied by the binomial u minus 1, all taken with respect to u. And at first glance, this still looks like bad news bears. But here's the important thing that we accomplished, everybody. In moving from here, the original integrand, to here, here's what we did. The original integrand was a monomial multiplied by the square root of a binomial. What we've changed it to is the square root of a monomial multiplied by a binomial. And that doesn't seem like a big deal, but it's huge. Why? Because we can now distribute that square root of the monomial into the binomial. Let me show you what that looks like. So this is now going to be a 1/25th multiplied by the integral of, and what's going on now, guys? The square root of u times u, that is u to the 3/2 power, minus the square root of u times 1 is the square root of u, or u to the 1/2 power. And we're integrating all of that with respect to u. So because we had the square root of a monomial multiplied by a binomial, the distributive property was now an option that we did not have right up here. You can't distribute this monomial into the square root of a binomial. That just doesn't work, but we are able to do a monomial, the square root of a monomial being distributed into a binomial. So let me do this, let me do that. Okay, and that's where I want it to be. So where are we now, everybody? So we're ready to go ahead and anti-differentiate. The 1/25th just tags along, and here we go. Integrating u to the 3/2 is going to be a u to the 5/2, and we have to divide by that new exponent. So that's putting a 2/5 out in front. Minus u to the 1/2 integrates or anti-differentiates into u to the 3/2, and dividing by that new exponent is going to put a 2/3 out in front. So we'll close all of that off, and don't forget a plus c at the end here, everybody, because this was an indefinite integral. Now we have to, I'm going to kill two birds with one stone. I'm going to redistribute here this 1/25th back in, and I'm also going to take out the u and put it back in terms of x. And I better remind myself that u, right here, you guys, u was equal to 5x plus 1. Okay, so where are we, everybody? 1/25th times 2/5, that's not pretty. That is going to be a 2 over a 1/25 multiplied by u, which was, dang it, I knew I was going to forget it again, 5x plus 1. There we go. I'm just not that bright. 5x plus 1, there's u to the 5/2 power. Minus, what now? Ugh, that's just a 2 over 75. The u again becomes a 5x plus 1 to the 3/2 power and a plus c at the end. And everybody, that is ugly, but it ain't getting any prettier no matter how long we sit here and stare at it. Okay, so that is our answer to example number 4. 4? Thought that was 4. Nope, 5. I lied. I can't count that high. All right. So that's where we're at with this one, everybody. Kind of an interesting problem, and you'll see one or two like that on your homework here. All right. And let's try to knock out one more problem here. I've got 7 minutes to do it before my next class. Let's see if I can get it done. Oh, yeah, actually, this one isn't that hard to do. It simply is an example of the type of problem out there that you don't see very often that I wanted to do this one with you here. So let's ask ourselves the same questions. First of all, I know I need a method right here. Why? Because differentiating the natural log of 5x over x, that would require the quotient rule because there's variables on both the top and the bottom. And if that's the case, then it's too complicated to simply reverse the process of anti-differentiation. So, are there two distinct parts to your integrand? Yes, there's a natural log of 5x on the top and an x on the bottom. Second question, is one of them the derivative of the other or somehow related to the derivative of the other? And that one, you guys, is a little bit tougher to see, but the answer to that is yes. We are going to let u equal part of the original integrand, but for the first time, we're going to do something different than we've done before. Let me take you back to the fractions we've seen so far here in example 2. Take a look at this problem. Look at your numerator. Look at your denominator. Where did u come from? U came from the denominator. Look at the next problem, the stan x dx problem. We changed it into sine of x over cosine of x, and for a reason we discussed, we let u once again come from the denominator, not the numerator. And I said something at that point that probably made you think, okay, anytime I've got the integral of a fraction, let u come from the bottom. Well, in this case right here, this is the one case with a natural log on the top where you're not going to do that. And I don't have a ton of time, so I'm going to go kind of quickly through this. We are going to let u equal the entire numerator, the natural log of 5x. Now, where does that get us? Let's see. So this integral is now equal to the integral of, and in our fraction, the entire numerator, natural log of 5x, has been replaced by u. What we now need to replace with our secondary substitution, and let's make sure we're reading this right, this is not x times dx, because that x is in the denominator. This is actually dx over x, or to look at it another way, 1 over x times dx. That's what I somehow need to get out of what's in green on the right. So let's try differentiating both sides. We're going to get the derivative of u is equal to, and if you recall, guys, the derivative of natural log of anything, a product, is 1 over that product, so in this case 1 over 5x, multiplied by the derivative of that product, which is 5, and then a dx at the end of all that. Well, sure enough, the 5's cancel, and right there, guys, 1 over x dx, that's what we needed for our secondary substitution. So the 1 over x dx can be replaced simply by a du. So the du goes right here, and with nothing on the denominator, technically I could put a 1 there, but now I feel stupid. U over 1, of course, is just u. That's it. This actually ends up being one of the easiest problems in this entire set of notes right here, guys. The integral of u is going to be a 1/2 u squared plus c, and then we replace the u with the natural log of 5x. So we'll get a 1/2 times the natural log of 5x quantity squared, gotcha, and a plus c at the end of all that, and we are good to go, ladies and gentlemen. And again, if I had a little bit more time right here, I'd walk you through this and take the derivative of what we just came up with. But I think you guys can see pretty quickly that, yeah, the 2 times the 1/2 is going to cancel, natural log of 5x to the first, times the derivative within. Derivative within, so where am I, guys? The 2 and the 1/2 cancel. This is a natural log of 5x, times the derivative within, 1 over 5x, and multiplied by a 5. The 5 here, the 5 there cancel, and yep, that's the original integrand. So natural log in the numerator, you guys, is the one spot you want to watch out for. That's where you probably would let u come from the numerator. And in just about every other case, you would want to let u come from the denominator. All right, guys, that's a wrap on our 5-7 notes on u substitution. Let's give that homework a try and let me know how you guys do. Good luck.